if you want to take a vacation, take it before that date, because who knows what will happen.
We're counting down the 7 most baffling mysteries of Atlas, the interstellar visitor that even NASA can't fully explain. From suspicious alignments and strange optical signatures to chemistry that defies all comet models, each item on this list pushes the boundaries of what we know about objects from beyond our solar system. The ranking goes from attention-grabbing coincidences to the deepest physical mysteries, sparking everything from missing photos to wild theories about hidden technology. Some claims are based on solid data, others on jaw-dropping speculation. But which anomaly ranks as the most inexplicable of all? Let's start the countdown at number 7. Number 7, the WOW signal connection. Atlas's incoming path passes within just 9 degrees of the legendary WOW signal coordinates, a detail that has fueled late-night debates and viral speculation since the comet's discovery. The WOW signal was a 60-second radio burst detected in 1977 by Ohio University's Big Ear telescope. It came from a precise point in Sagittarius, like a cosmic beacon flashing just once. Its beam was less than 1 degree wide, like a laser pointed across space. But the comet's approach lands just outside that narrow window in the same general area of sky. It's a proximity that sounds haunting at first glance. 9 degrees is less than 1% of the celestial sphere, like finding 2 people in the same city in an entire country. However, in astronomical terms, it's not close enough to suggest any physical connection, like 2 cars passing on the same highway, but on different days. No repeat of the WOW radio burst has ever been recorded, and the vast gulf of time and space between the 2 events makes a direct connection nearly impossible, like trying to connect 2 events separated by decades and light years. Still, the coincidence has proven irresistible, appearing in podcasts, message boards, and even research preprints, like a story people love to tell, even knowing it might just be coincidence. Statistically, with only 3 known interstellar visitors, any directional overlap stands out, but astronomers warn against reading too much into it. With thousands of possible sky alignments, patterns like this are bound to emerge by chance, like finding shapes in clouds after looking long enough. The WOW region overlap is a textbook case of what statisticians call post hoc selection bias, the human tendency to notice matches only after the outcome is known. It's an appealing detail, but with no diagnostic power, just a cosmic coincidence that keeps the mystery alive, like a song that sticks in your head even without meaning anything special. Number 6, the impossible orbital alignment. Atlas's orbit cuts nearly flat through the solar system, like a coin sliding perfectly across a table. Its measured inclination at just over 3 degrees above the ecliptic is a razor-thin alignment in astronomical terms, like a plane flying at exactly the right height to land on a runway. For context, most interstellar objects arrive at steep angles, plunging from far above or below the solar plane, like planes arriving from all directions at an airport. Oumuamua crossed at 122 degrees, Borisov at 44 degrees, both on sharply tilted paths like cars entering a highway from very steep ramps. Here, the trajectory hugs the same disk where planets travel nearly parallel to Earth's own orbit, like a car entering perfectly into a highway lane without needing to change direction. Statistically, the chances of a random interstellar visitor arriving within 5 degrees of the ecliptic are less than 0.5%, like hitting a very small target from very far away. Calculations from the Minor Planet Center and JPL Horizons confirm the measured inclination, 3.18 degrees, with uncertainties under a 20th of a degree. Numbers as precise as a cooking recipe measured with a digital scale. Under standard models, only about 4 in every 1,000 interstellar objects would be expected to match this alignment by chance, like finding 4 left-handed people in a crowd of 1,000. Some astronomers point to observational bias. Earth-based surveys are more sensitive to objects crossing near the ecliptic, like spotlights that illuminate certain areas better. But even accounting for this, the flat approach stands out. With only 3 confirmed interstellar visitors so far, the pattern is hard to ignore. The geometry raises questions. Is it coincidence, selection effect, or a clue to deeper dynamics? Like 3 dice that always land showing similar numbers. Technically possible, but suspiciously unlikely. Number 5, the strange light polarization. Polarization tells astronomers how light scatters from a comet's dust, revealing the size, shape, and composition of those grains, like cosmic dust fingerprints that tell us what it's made of. For Atlas, initial polar reports triggered debate across the field, like scientists arguing about a discovery that doesn't make sense. Observers using the Nordic Optical Telescope and Gemini North recorded polarization values that remained strongly negative, even at phase angles where most comets flip to positive. At a Sun comet, Earth angle of 30 degrees, the measured polarization plunged below -2%, an extreme reading for any comet, let alone an interstellar visitor. Normally, comets show negative polarization only at small phase angles near zero, with the signal flipping positive as the viewing angle widens, like the difference between looking directly into a mirror versus from the side. The inversion point where polarization crosses zero typically falls near 20 to 25 degrees, like a rule that almost all comets follow, like traffic lights that always change from red to green in the same sequence. Moreover, a typical comet's dust scatters light in a way that aligns perpendicular to the incident sunlight, like light reflecting off a water surface. Here, Atlas's dust seems to do the opposite, maintaining negative values well beyond the expected threshold, like a mirror that reflects light in the wrong direction. Instrument teams checked for calibration errors, atmospheric interference, and even scattered light from Mars, but the numbers held like a thermometer that keeps giving the same strange reading even after being tested multiple times. The effect was repeatable across multiple nights and different telescopes using R and V band filters, like an experiment that gives the same bizarre result every time it's repeated. Such persistent negative polarization suggests dust grains with unusual structure, perhaps large fluffy aggregates or a composition richer in carbon or complex organics than most solar system comets, like cosmic snowflakes instead of normal sand grains, delicate, complex structures instead of simple chunks of rock. Number 4, the impossible chemistry. Spectroscopic surveys of Atlas revealed a chemical fingerprint that refuses to fit the standard comet model, like finding ingredients in a recipe that simply shouldn't be there. Initial spectra from ground-based telescopes showed strong emission lines from neutral nickel at 3.414 angstroms, while the usual iron signatures were nearly absent, like finding lots of gold in a mine, but almost no iron. In typical solar system comets, nickel and iron appear together, their lines rising and falling in tandem as the nucleus releases metal-rich dust, like twin siblings who always walk together. Here, the nickel lines were clean and persistent, but iron lagged behind background noise, barely detectable even in stacked exposures, like trying to hear someone whispering in a noisy room. The signal-to-noise ratio for nickel crossed the threshold for robust detection, like a clear, strong radio signal. Yet iron remained stubbornly weak, an imbalance not seen in previous cometary spectra. Like finding a cake recipe with lots of sugar but no flour, the ingredients simply don't make sense together. Analysts combed through the raw data, checking for calibration errors and atmospheric contamination, but the pattern held across multiple nights and instruments, like detectives checking evidence multiple times and always finding the same strange thing. The standard cometary bands C2 and CN were present but moderate, suggesting a dust and gas mixture richer in metals and poorer in volatile organics than most known comets. This composition, if confirmed by follow-up with the James Webb Space Telescope, would mark a sharp departure from the norm, like finding an animal that doesn't fit into any known category. Metal-rich, iron-poor comets are rare even in the outer solar system and virtually unknown among interstellar visitors, like finding a person who has lots of calcium in their bones but almost no iron in their blood. The chemistry has implications for both the object's origin and its optical behavior. Unusual metal ratios can alter how sunlight scatters through the coma, changing both color and polarization. Like different spices changing the flavor of food, small changes in composition can create big differences in what we observe. Number 3, the sun-facing jet. Atlas's most visually striking feature is a plume that appears to flow forward toward the sun, a geometry that turns the textbook image of a comet upside down. In standard cometary physics, the solar wind sweeps dust and gas away from the nucleus, sculpting a tail that always points anti-sun, no matter which direction the comet moves, like hair blowing always in the direction opposite to the wind. But here, time series images from Gemini South and the Nordic Optical Telescope captured a faint fan-shaped extension flowing toward the sun, almost as if the comet were venting vapor from its leading edge. Like a car with the exhaust in front instead of behind, a configuration that simply doesn't make sense according to everything we know about how cars or comets should work. The effect isn't just a trick of the eyes. Analysts tracked the plume's orientation across multiple nights, accounting for the comet's rotation and the changing angle of sunlight. The forward jet held steady even as the overall coma brightened and the main tail began to unfurl behind, like a feature that stubbornly refuses to behave as it should. Projection effects can sometimes reverse a tail's appearance, creating so-called anti-tails when Earth's line of sight cuts through the comet's orbital plane. But here, the geometry defies easy explanation. Like a puzzle where the pieces simply don't fit no matter how you turn them. The plume's alignment with the Sun-comet axis persisted through a range of phase angles, resisting the usual explanations tied to perspective or orbital tilt. Like an arrow that always points in the same direction regardless of how you look at it, a behavior that defies our understanding of how objects in space should behave. Some researchers pointed to rare precedents, comets with active vents near the subsolar point or with jets triggered by buried pockets of volatile ice, but even these cases rarely produce such a distinct forward fan at this distance from the sun, like finding an exception to the exception, something that's rare even among rare things. Number 2, the giant size. Atlas's size stands out as its most shocking statistical deviation, like finding a giant in a family of dwarfs. Initial photometric modeling based on its coma brightness and the faint glow of the nucleus itself returned a diameter near 5 kilometers, more than 3 times wider than either of the previous interstellar visitors. Mass calculations anchored in standard albedo assumptions and the observed rate of sunlight reflection produce an estimate above 33 billion tons. By every measure, this is a heavyweight, a body that outclasses not just Oumuamua and Borisov, both under a kilometer, but nearly every comet ever seen entering from outside our solar system. Like finding a blue whale in a school of small fish, the size difference is so dramatic it makes you question whether they really belong in the same category. Avi Loeb and his colleagues at Harvard flagged this as a major anomaly. According to prevailing models of interstellar object populations, for every giant like Atlas, there should be hundreds of thousands of smaller fragments. Pebbles, boulders, even city block-sized chunks crossing the same cosmic highways, like a pyramid where the base should be much larger than the top. Yet in the years since, surveys like Pan, STARRS, and Atlas began sweeping the skies, only 2 small interstellar objects were cataloged before this giant. Like finding a whale before seeing any minnows, a sequence that goes against everything we'd expect to encounter. The expectation based on stellar debris physics and ejected body statistics is clear. Large are rare, small common, and the chances of detecting a giant before the swarm of pebbles approach 0. Instead, the first 3 interstellar objects found by humanity form a lopsided sequence. Small, small, then suddenly massive. Like finding 3 cars and the third one being a giant truck, a progression that simply doesn't make statistical sense. Number 1. The impossible trajectory. Atlas's most improbable anomaly unfolds in its planetary passages and the remarkable stability of its path, like a dancer executing perfect choreography without ever having rehearsed. On the 3rd of October 2025, the comet passed Mars at a distance of just 28 million kilometers, a near miss in cosmic terms, like 2 cars passing within inches on the highway. Orbital analysts at the Minor Planet Center and JPL ran Monte Carlo simulations to estimate the chances of such an approach for a random interstellar object. The answer? Less than 5 inches, 100,000. That's below 0.005%. The numbers aren't just low, they're nearly off the chart for casual alignment. Like winning the lottery, but with even worse odds. The kind of event you'd expect to see maybe once in several lifetimes. The geometry complicates the puzzle. The comet's low inclination orbit hugging the ecliptic set it up for a chain of planetary encounters. First Mars, then a projected close pass by Venus, and later a distant approach to Jupiter. Each passage would be rare on its own, but the sequence timed and spaced with such precision strains the limits of statistical expectation, like hitting the lottery 3 times in a row. The trajectory was locked in the moment Atlas entered the solar system, like a train following tracks that were laid long before anyone knew the train was coming. But the anomaly doesn't end with geometry. As the comet approached the sun, astronomers expected its outgassing jets, venting up to 150 kilograms of ice and dust per second, to act like thrusters, pushing the nucleus off its predicted track. For most comets, these non-gravitational accelerations are measurable and often dramatic, like a boat being pushed by the wind. Borisov, the previous interstellar visitor, showed NGA changes near 100 kilometers per day, like a car that constantly changes lanes. Hale-Bopp, a solar system giant, registered over 10 kilometers per day at peak activity. Atlas, in contrast, barely budged. Through months of astrometric tracking data from 227 observatories worldwide, the reported NGA stayed below 15 meters per day squared. Like a cruise ship that doesn't move even in a storm, a stability that defies our understanding of how objects in space should behave when they're actively releasing material. This is less than 0.1% of Borisov's deviation and orders of magnitude below the wild swings seen in Oumuamua. The comet's path remained a ruler straight arc through space, unaffected by the jets boiling from its surface, like a bullet flying in a perfectly straight line, even with strong winds blowing from all sides. The only way to reconcile such minimal deviation, given the measured outgassing, is with mass. Immense mass. The nucleus, estimated at over 33 billion tons, absorbs the force of its own jets without flinching, like a freight train rolling through a gust of wind. Some theorists, led by Avi Loeb's group at Harvard, see a different possibility: orientation. When the passage sequence, ecliptic alignment, and unwavering trajectory are stacked together, the result is a case study in improbability. Could a natural object, however massive, thread such a needle by chance? Or is there a deeper mechanism, unknown physics, or even intention at work? Like a basketball player who makes impossible shots repeatedly. Technically possible, but so unlikely that you start to suspect something else is happening. What it all means, from the curious overlap with the famous wow signal to the hauntingly stable and massive trajectory at the top of our list, these 7 anomalies make Atlas stand apart from any comet we've ever seen. Across all entries, a pattern emerges. Atlas consistently defies expectations, like a student who always gives correct answers to questions that were never taught. Whether it's its nearly perfect ecliptic alignment, rare chemistry rich in nickel but low in iron, or the sun-facing jet that defies textbook cometary behavior. Yet it's the combination of a giant nucleus 5 times larger than previous interstellar visitors and its improbably optimized planetary passages with minimal non-gravitational acceleration that truly sets it apart. Each item earned its place by being statistically rare or physically intriguing compared to known comets and even other interstellar objects. Together, these anomalies reveal how little we understand about what drifts between the stars and how much discovery still awaits us, like realizing that a book we thought we'd read completely still has entire chapters we've never seen. Atlas isn't just another space rock, it's a reminder that our solar system remains open to cosmic surprises and that the universe still has many secrets to tell us. Like a mystery box that keeps revealing deeper layers of complexity every time we think we understand what's inside. The question that remains isn't whether Atlas is strange, that's already clear. The question is whether its strangeness points to natural physics we don't yet understand, or to something that will fundamentally change our understanding of what's possible in the cosmos. And perhaps, just perhaps, our understanding of whether we're truly alone in the universe